Hello everyone, and thank you for joining us. Today I want to tell you about quantum orchestration, for quantum error correction, and in particular focus on the importance of having a platform that allows to easily program quantum error correction from software while not compromising on the hardware performance that is so critical for quantum error correction. So before we dive into the technical details of quantum error correction, let me put an even broader context to motivate the discussion. Today in quantum computing, we're seeing two critical parallel efforts, which I will call the two races of quantum computing. The first race is the race towards quantum practicality, which focuses on demonstrating the value of quantum computing in the near term on NISQ processors. This race is of course very important because only by showing real value in the relatively near future, we can continue to push the field quantum error correction protocol successfully. And it is of critical importance because this is what will allow us to realize the full-blown potential of quantum computing in the long term. At QM, we're pushing in both of these directions very strongly. Today, we want to focus specifically on how this approach is relevant for the second axis here, which is the race toward fault-tolerant quantum computation. I think the word race here is appropriate because it's really important to maximize how fast we make progress towards fault tolerance. And here we should really note the technical subtleties that are critical for quantum error corrections, because these technicalities make developing quantum error correction fast very challenging. You see, while quantum error correction is clearly one of the most important focus areas of the field, it is also one of the most difficult areas. On the one hand, it requires working at very low level with quantum machines and controlling quantum and classical operations with precise timing control and on the nanosecond level. Here we see that the quantum controller, which orchestrates the pulses sent to the QPU to perform quantum operations and measurements on the QPU as well as real-time classical compute operations that happen during the quantum circuit itself and actually affect it. And on the other hand, the road is long. There is so much more learning and exploration to do in the next several years regarding on how to best run quantum error correction protocols that it is not good enough to build right away a super specific hardware that is maybe optimal for running very specific types of quantum error correction. New variation in the protocols and new protocols come up all the time. And we must have a short cycle for trying out ideas, for learning from them, and repeating this process and many times as fast as possible. It is therefore critical that we build tools that allow us both to program at low-level quantum and classical operations with precise timing control and squeeze performance from the hardware, and at the same time allow for fast and flexible development and exploration of new ideas. And this is precisely what the quantum orchestration platform enables. What is fault-tolerant quantum computing? So let's take a step back and talk about what is fault-tolerant quantum computing and what is quantum error correction. So if we look at classical computers, they typically don't make mistakes. If we ask a classical computer what are the prime factors of 15, we can be very certain that it will tell us that they are 3 and 5. There is an algorithm to do this. Even if it is not very efficient as we know, there is an algorithm that will most definitely give us the right answer. So classical computers do not make mistakes, almost. Every now and then you get a blue screen of death. There are so many classical computing devices today on Earth that one of the common reasons for blue screen can actually be a cosmic ray that produces an error in the device. But this is of course very rare. So the error rate in typical classical computers is of the order of 10 to the minus 18. And the biggest problem with quantum computers and qubits is that they are very sensitive to noise from the environment. And the error rates of qubits are at the 1 to the minus 3 level. Okay, that means that whenever we do an operation on a qubit, there is a 1 in 1,000 chance that this operation will be erroneous and it will corrupt the data. Okay? And actually, there are two types of errors in quantum computing. There is bit flip, which turns a logical a 0 state into a 1 state. And there is a phase flip, which changes the sign between the plus sign to a minus sign in the superposition state of the logic of the qubit. So quantum error correction aims to solve this problem by encoding quantum information using a system with a redundancy of qubits or quantum states in combination with classical control and compute to create logical qubits that are protected from errors. In other words, quantum error correction protects quantum information by storing it non-locally in the correlations between the states of many qubits in a way that allows local errors to be detected and corrected. For example, we can encode a single logical qubit with 3 physical qubits as shown here. So you see here that instead of storing the amplitudes alpha 0 and alpha 1 in a single qubit, we store them in these two states of a 3-qubit system, alpha 0 times 0, 0, 0, and alpha 1 times 1, 1, 1. And if one of the physical qubits flips by some unknown local error process, we can actually correct for it. You can see pretty clearly that because even though the third qubit is flipped, the majority of the qubits are still in the correct state. But importantly, we cannot simply measure the qubits and do majority voting, because this will collapse the state and we will lose the information. And instead, we want a clever way to discover what errors happened. And in this example, this can actually easily be done by measuring the parity of pairs of qubits. We measure here the parity between the first and second qubit and between the second and third qubit. And we see here that before the errors, the two parities were even, okay, meaning that 0 and 0 are the same, or 1, 1 are the same. And after the error, the parity of the second and third qubits changed to odd, because now we have 0 and 1 and 0, so they're not the same. And so from the two parities, we can actually infer which of the 3 qubits was flipped. And this combination of the two parities from which we can extract the error is called the syndrome. And if from measuring the syndrome and how it changes, we can infer what errors occurred and correct them in real time using fast control. But this is very hard. To begin with, we must be below a certain error rate, a threshold on the physical qubits, in order to run quantum error corrections successfully and create the logical qubits, because we must manage to track the errors faster than they arrive. In fact, every quantum error correction protocol would require a different threshold, and the ones that are least demanding, like the surface code, require error rates that are better than 10 to the minus 2. In addition, we need extreme real-time control capabilities with real-time classical processing and ultra-low latency feedback that are needed for tracking errors, adapting syndrome measurements, correcting errors, producing magic states that are important for performing gates on logical qubits, and more. So quantum error correction is very hard. In fact, the first demonstration of quantum error correction was done by no other than our chief engineer and one of the founders of QM, Nissim Ofik. And here you can see just how complicated a control diagram was needed to run for the very first demonstration of a single logical qubit, not yet performing gates between logical qubits and scaling up. At QM, we are focused on the control stack of quantum computing, and our goal is to bring the best out of any QPU and allow achieving fastest time to results in quantum development. In our control hardware stack, we have our highly scalable and modular analog front end, which produces the signals that drive the QPU dynamics, and then the heart of our technology, which is the pulse processor. This is a new type of processor that is designed for quantum control, and it is responsible for generating the pulses and quantum measurements in the digital domain, for sequencing and orchestrating the entire quantum program, and for real-time classical compute resources. This is the first key component to random quantum error correction. And the second key component is the interface to our system, which is QA, a first-of-its-kind programming language that allows programming quantum operations and classical operations in the same code so that they run together with precise timing control and affect each other. This is what makes programming quantum error correction so easy and flexible. Finally, we have integrated into the hardware many important components, such as co-processors, stream processing capabilities, high bandwidth networking, storage and caching, and more. And so all of this works together to really provide a complete solution for quantum error corrections. In fact, on top of this, in our software layer, we have our integration with higher layers, including our integration with OpenQASM 3, which we'll be releasing early in 2022, and Entropy, our calibrations and QPU abstraction platform, as well as many OS code libraries we're developing with our customers. But for quantum error correction, the most important components are the pulse processor and QA. It is exactly this combination that allows programming quantum error corrections as intuitively as writing pseudocode, while getting real-time control and hardware performance that is the best in the field. So just before we look at examples of programming actual quantum error correction, here is an overview of some of the main components of QA, which allow such programming. Okay, so first, we can play pulses to the elements in the quantum processor, as well as perform measurements, of course. These are the quantum operations. Second, we can define completely general classical variables like A and B here, and we can perform completely general classical processing with these variables, and we can use them in our circuit. And this is really what makes QA unique, as mentioned. It interleaves classical operations and quantum operations in the same code, all running in real time. This is shown in the next point, where we can use these classical variables as the parameters of pulses. Here we modify the amplitude or the duration of a pulse according to the classical variables. Now, another critical component of these classical variables is that these classical variables can also be fed by the measurements of a quantum system. So here we measure a qubit or a resonator, and the result goes into a variable I, and which we can then continue to process. So you see here we say state, which is another variable, a Boolean variable, which equals I larger than some threshold, which is actually state discrimination. And next, we can do control flow, which again can be based on the classical variables. So for example, if state, we play a pulse, or while we measure some error syndrome, we keep doing something, etc. So you can see now that feedback becomes trivial with QA, since you can simply measure your qubit into a classical variable, and then use this variable for control flow or for modifying pulse parameters. Finally, we have full timing control with sync and asynchronous multi-threading. Okay, so let's look at some examples of programming quantum error correction with QA. We will look at the repetition code, similar to shown in the Google work from earlier this year. Then we will look at magic state preparation, a la AWS in their concatenated CAT codes from paper from 2020. And finally, we will look at adaptive error syndrome measurements by Honeywell from their publication earlier this year. Okay, so let's first look at the repetition code. The repetition code is a relatively simple code that in fact does not correct for all quantum errors. It can be thought of as a prototype for the more complex surface code, but even from this very simple example, we can already get a good sense of the control challenges it brings with it. So here is a scheme showing the quantum circuit of the simplest repetition code, the distance 3 repetition code, which means it can correct for only one bit flip. As you can see, we actually need 5 qubits because we have 3 data qubits, and there are 2 additional measurement qubits, these 2, that are used to perform the parity measurements discussed earlier. We see mid-circuit measurements that must be performed during the circuit. And we see error decoding and tracking that is done in real time. Moreover, this error tracking needs to be repeated with a minimal repetition cycle time to improve the error budget, so you want to decode errors as fast as possible. Second, we typically want to reset the measurement qubits every cycle. And third, when we correct for the errors, feedback-based control that is based on the classical processing of the error tracking must be employed. So here is the QA code, which is simplified a bit for the error tracking part. We have the C-naughts and the measure statements defined somewhere else with their pulse sequences and measurement operations. And then here's the most important part, where we process the results of the ancilla qubit measurements and based on them track the errors. As you can see, this is written in the same code with the C-naughts and the measurements. Okay, so it all happens together. Then we can simply add the correction part at the end by performing these if statements. So we say if the first qubit is flipped, we play a pi pulse to it and flip it back and so on. Similarly, we can easily add a reset of the ancilla qubits just by adding flipping pulses operations to the relevant ancilla qubits wherever it is needed. So you can see how easy and flexible it is. In fact, one thing that was not done in Google's work is adaptive syndrome measurements, where based on the previous measurement, we slightly change the parity measurement protocol in order to improve readout fidelity. I will not get to it in too much detail other than to say that we're currently developing such protocols on QM, and that we'll hopefully publish it soon. The point again is that we can easily program such adaptive protocols with a few lines of code from QA. So this was the repetition code. And our next example is magic states preparation. And specifically, the EC stop algorithm from the AWS concatenated CAT codes paper. So here on the right, you see the pseudocode of the stop algorithm that includes complicated things like repeat until success, and a lot of control flow based on real-time processing. And here is the pseudocode from the paper itself. And here is the QA code, which in fact highly resembles the pseudocode. you can see the while loop here, and the if statement with the classical variable assignment here, and the measurement with another classical assignment, and another if statement with classical processing. Basically, this protocol is a great example for combining all elements we mentioned today very nicely. Okay, so the last example I wanted to mention is that of the adaptive error syndrome measurement published by Honeywell earlier this year. Here you can see, for example, this encoding circuit and how it gets translated into QA. And then this logical operation circuit. And here you can see this flow chart that has conditional operations on it. And here you see how this flow chart is created in QA. You see that it looks very, very similar. It's basically just pseudocode. Here we see the logical operation that we apply at the end of the cycle and the final measurement in the decoding. And all can be basically implemented directly in QA. Although we're not showing the code, we're just showing the macros that create this code. All of the code can be created directly in QA. All right, I hope I was able to demonstrate to you how powerful the combination of an intuitive programming language that is highly connected to the control hardware and allows to program at the real-time level both quantum and classical processing. Before I finish, let me just mention that beyond the real-time capabilities, the integration with heavier and more general classical processing resources could also be important for quantum error correction, at least in some qubit platforms. For example, one could think of doing some of the error tracking on powerful classical resources. For this, several components that have to be added to our hardware stack are important. Two examples here would be co-processors, which, for example, can increase the processing power and proximity to the QPU and allow better error tracking of more and more qubits. And streaming, which allows sending measurement results during the runtime of the quantum error correction to classical compute resources. Once more, I hope that I was able to demonstrate to you today that the quantum orchestration platform can really open up possibilities for research and development of quantum error correction, and that the race for fault-tolerant quantum computing of the upcoming years, it will allow us to move fast and learn fast towards the milestones ahead. Thank you very much.